Hi. Now we established how complementary function of the case of complex roots look like. We can actually try to assess the stability of equilibrium. Okay, but before we do so, let me just do a very simple exercise that's gonna lead us on a proper path of the examining dynamic stability of equilibrium. Okay, let, for example, A5 be equal to some A cosine epsilon. And the same with A6 is equal, now A6 is equal to negative sine epsilon. Okay, let's just use this part of the complementary function, and let's see what happens once we use those results. Because assuming that we get that A5 cosine Vt plus A6 sine Vt is equal to, we get that this is A cosine epsilon times cosine Vt plus, so minus A sine Vt, let's put it like this, that's sine epsilon cos sine Vt. And look, we clearly see that A over here can be taken out of the parentheses. And what do we get? Inside we've got A cosine epsilon cosine Vt minus sine epsilon sine Vt. A couple of videos ago, I actually described to you this trigonometric identity. I hope you remember this one. Cosine theta 1 times cosine theta 2 minus sine theta 1 times sine theta 2 is equal to cosine theta 1 plus theta 2. Okay, so what does it imply for us? That we can write this as A times cosine Vt plus epsilon. Okay, why is this important to us? Because look, you know how cosine looks like, you know like how sine looks like. But what happens when we combine them? Look, actually, what we can see from this example is that if you have a sine function and if you have cosine function and you are combining them, what you get is another cyclical function that can be represented as one of them, right? As a special case of cosine. Okay, so this actually tells us that when we talk about complementary function, this part is just going to give us fluctuations, right? So this part is going to be responsible for making waves. However, there is another part that we've got over here, right? We've got this e to the power ht. And how does this gonna work? Look, this actually resembles what we already had in all the previous considerations with second order and first order differential equations. Look, what we get from EHT is scaling effect. Because look, if h is positive as t it goes to infinity, we get that in this case, if h is positive, limit with t approaching infinity out of eht is going to be infinity. This function is going to be ever increasing. Now, if h is lower than 0, limit with e, what do we get out of it? Right now, look, if h is lower than 0, it means that as t becomes bigger and bigger, here we have a minus, right? So we divide 1 by e to a bigger and bigger and bigger and bigger power. It dies out to 0. Right? And finally, we might have a case of h equal to exactly 0, and then the limit with t approaching infinity, which is actually not needed even here, is this, right? It's a constant. It's always 1. And look, these are actually the 3 cases that we might have. Look, in the first case, we will see some magnifying effect, right? That this expression will make whatever is in the parentheses bigger and bigger and bigger. Over here, it will make it smaller and smaller and smaller. And finally, if h is equal to 0, we are left with just the expressions for fluctuations. So how do they look? Okay, let's consider 3 different possibilities here. Okay, first, let's consider that h is equal to 0. Okay, so this is the graph. Let's just say that here we have time, here we have value of y, and this is our particular integral, so equilibrium values. And let's just say that at time 0, our variable is out of the equilibrium, just by little. What will happen then? Well, we get it just by looking what happens to this sum of sine and cosine, right? So we will see a fluctuations, uniform fluctuations, like that. Well, we should have here the same from the bottom and the same from the top. So look, this case we will call uniform fluctuations. And what do we see that actually happens? What actually occurs over here? We see that once variable is thrown out of the equilibrium, the function fluctuates around this equilibrium forever. It never goes back to equilibrium level. It just fluctuates around it. So, in this case, we say we have non-convergence. Or dynamic instability. Okay, now what happens if h is bigger than 0? Look, now we have the case that expression EHT gets bigger as time progresses, right? Let's draw this one. Well, here we have y. Here we have some yp, so our particular integral, the equilibrium solution. And let's see what will happen over here. Look, here we will have the situation. Let's just say we start here. The fluctuations will be very, very small, but as time progresses, they're going to be getting bigger and bigger and bigger and bigger and bigger and bigger. So again, we are observing that actually now value of y is fluctuating around the equilibrium, but because h is bigger than 0, which means that EHT is getting bigger and bigger and bigger with time, we actually are observing divergence. This case we're going to call explosive fluctuations. So we see that even though we are going through the equilibrium value from time to time, we are actually getting further and further away from it in terms of the tops and bottoms, peaks, so the upper and lower peak of the function. So in this case, we talk about divergence. And again, dynamic instability. Of equilibrium. Okay, finally, we will have a case number 3. In a case number 3, of course, h is going to be smaller. It's going to be smaller than 0. So it's negative. So finally, we've got the case where h is smaller than 0. Let's draw this one. Again, we have some equilibrium value. And what happens over here? Look, now expression e to the power ht becomes smaller and smaller and smaller as time progresses, right? Because this is the case where we divide 1 by e to the power negative ht, right? Because we are assuming that this is negative, so this is positive. So we are dividing here by a bigger and bigger number. So it dies out. So how will this look? Let's just say that we start from this point, and we will have something like this. The fluctuations still appear, but they get smaller and smaller and smaller and smaller and smaller, and eventually, as enough time passes, we are getting back to equilibrium. So this case, we're going to call damped fluctuations. And this is the situation in which we will have convergence and dynamically stable equilibrium. Right? So look, if we want to assess dynamic stability of equilibrium, all we need to look at is actually h. Remember, h is negative a1 over 2. Just looking at the value of that will tell us whether we have a case of uniform fluctuations, explosive fluctuations, or damped fluctuations. Okay, at this moment, we know everything we need to know about second order differential equations with constant coefficients and constant term. So, now that we know how to handle them, the next thing is how to apply them in economic context. And this is going to be a topic of our videos next week. Thank you for your attention.